For this one, we have a pretty classic situation of optimization problem where we've got a square piece of cardboard and it does tell us the side length is 60 inches for each side. So this is 60 inches, okay? And then we are trying to fold it into a rectangular box with a lid. So 4 squares of side length X, so these white spaces here, and then the 2 rectangular regions are going to be cut out and discarded to make the box. So we are trying to maximize the volume of the box with what is remaining, okay? And again, we're cutting off squares that are X by X here, so we need to figure out how to maximize, we want to maximize the volume. All right, so this is a volume of a box or a rectangular prism, which is length times width times height. But we need to figure out how to get all of those in terms of the single variable. So step 1, variable to be optimized is going to be volume. And we have an equation for volume, length times width times height, but now we need what are all of those in relation to each other. And that's where the other information comes in. So we know that the side length of the whole piece of paper, whole piece of cardboard is 60. And we are cutting, let's start with this left side. We are cutting X off of each side, which means that this remaining amount is going to be 60 minus 2x because I'm cutting that off of each side. Okay. Similarly, this, let's see, this right here is going to be a total of 60, but we are subtracting x twice. So I'm going to say minus 2x. And then I'm also subtracting this part. Well, I'm not entirely sure what this is in terms of x, but I do know that this rectangle here and this rectangle here are the same. So if 60 minus 2x is the long rectangles together, I'm going to divide that by 2 to get the length. Oops, sorry, I shouldn't have put that there. To get the length of just this part, okay? So this shaded part right here, or the side of the box, is going to be 60 minus 2x all over 2, which is the same as 30 minus x, okay? And then lastly, the third dimension is going to be the height of the box, and that's the amount that gets folded up, or the height that gets folded up, which is going to be x because it's this right here or this right here. So hopefully you can kind of visualize how this is getting folded up. This side on the left and this piece right here are being folded up. These two are both being folded up from the top and the bottom, and then this part will flip over and cover the top of the box, okay? So we have our 3 dimensions. And they are going to be the 60 minus 2x, which is the base length of the box. 60 minus 2x. The base width of the box is 30 minus x. And the height of the box is going to be x. So we now have everything in terms of a single variable. I'm going to go ahead and distribute so that I don't have to use the product rule. And so that's going to give us 1800x minus, and that's going to be 60 minus 60. So minus 100 and, oh, sorry, that should be x. No, yeah, just x. Minus 120x squared, and then plus 2x cubed. Okay, and if you want to rewrite it with the, in descending order with the highest degree first, that's fine. Okay, so that's the algebra part. We now have a variable volume that is in terms of a single variable x, and we can do the candidate test at this point. So v prime is equal to, and I'll rearrange it because it'll be easier to factor. So 6x squared minus 240x plus 1800, and then we'll set this equal to 0. I do have a common factor of 6, so let's get rid of that. X squared minus, 40x plus 300 equals x. That factors as x minus 10 and x minus 3. So x equals 10 and 3. All right, so we do have a couple of options, and now we need to figure out which one is going to give us the maximum volume. So I'm going to plug both of those. I'm doing just a candidate test here. I'm plugging both of those back into my original volume function. You could plug it into here. That's more computation than I want to do, so I'm going to plug them in to here. Okay, so x and volume. We're going to check 3 and 10. And again, we don't need to worry about endpoints. My natural domain would be from 0 to 30 because I can't have a side length less than 0. And I'm looking at this 60 minus 2x or the 30 minus x. If x is equal to 30, we basically have cut everything, and so there's no box. So these are the only two that I really need to consider. Okay, so if I plug 3 back into this, I have 60 minus 6 is going to be 54 times 30 minus 3, which is 27, times 3, which is going to be 54 times 27 times 3, 4374. I just did it on a calculator here. Okay, and then if I plug 10 in, I'm going to have 60 minus 20 is 40, times 30 minus 10 is 20, times 10 is 8 with 3 zeros, 8,000. So my maximum volume then is going to be 8,000, do we have units? Yes, inches. So 8,000 inches cubed is my maximum volume. Okay? All right, number 4, which point or points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So again, I'm going to go ahead and graph my parabola, 4 minus x squared. So this is y equals 4 minus x squared. And then x-intercepts of -2 and 2. All right, so we want to know which points on the graph of this are closest to the points, or to the point 0, 2, which is going to be this point right here. So for any point that's along this curve, I am looking for the distance from 0, 2 to that point. And I'm going to call this point xy. Again, if you want to use something like AB to pick different variables, you're totally welcome to do so. So I'm trying to minimize that distance. So I want to minimize the distance, and distance, I'm using distance formula, so that's going to be x minus 0 squared plus y minus 2 squared. Now, this distance formula, minimizing distance formula, will come up. So here's my very strong suggestion. Whatever point makes my distance the minimum is the same point that will make the square of the distance a minimum. The distance won't be the same because I will have a number that is squared from what the actual distance is. But the point that I find, like my critical point, is going to be the same. So what am I saying by that? I can, instead of using lowercase d, which is distance formula, I'm going to say that d is equal to lowercase d squared, and call this x squared plus y minus 2 squared, because this, I still need substitution to get everything in terms of x, but I don't need to take the derivative with the chain rule with the everything to the 1/2, which is going to be quite a bit messier, and instead I can find the point that minimizes the square of the distance, and then if I need to know what the actual distance is, I'll just make sure to take the square root of that. Okay, so this is now the thing that I'm going to try and minimize, and I do need to do some substitution. I know that y is equal to 4 minus x squared, so I can replace y with 4 minus x squared, which gives me x squared plus the quantity 4 minus x squared minus 2 squared, which becomes x squared plus, so 4 minus 2 is a 2. The quantity 2 minus x squared squared, I can stop here and I can do the chain rule with my derivative, or I can go ahead and just expand that. So 2 squared is going to be 4, and then minus 4x squared and plus x to the 4th, which, once all the like terms are combined, is x to the 4th minus 3x squared plus 4. So that's my new square of the distance formula. Now I'm doing the calculus part, which is the candidate test. I'm going to take the derivative. So we get 4x cubed minus 6x, set this equal to 0. I can divide everything by 2. I'm just going to factor it out, not a big deal. And so I have, 2x squared minus 3. So x equals 0, and if I set that equal to 0, I get this plus or minus the square root of 3/2. Okay, so then those are my critical points. And I will say again, this is similar to the one that happened on this problem right here with the plus or minus. Because it's a parabola, we have symmetry as far as whether the x is to the left or to the right. So I don't need to check both of these because I'm going to get the same distance no matter what. And if you look at the exponents, all of these are even. So plugging in a positive root 3 over 2 or a negative root 3 over 2 gives me the same thing. Okay, so candidate test. I'm testing at x equals, x equals 0 and root 3 over 2, again, because plus or minus doesn't matter there. If I plug in 0 back into my distance formula, or my square of the distance formula, and again, I can use this one, or I can use it. It doesn't really matter where I plug it in. I'll plug it in here because that'll be easy. I'm going to get a 4. If I plug root 3 over 2 in here, I get root 3 over 2 to the 4th, which would be 9 over 4, minus 3 times root 3 over 2 squared is 3/2, plus 4. So that's going to be 9 over 4 minus 18 over 4 is negative 9 over 4. I'm going to come down here. Negative 9 over 4 plus 16 over 4 gives me 7 over 4, which either way is less than 0. So, oh wait, hold on. Nope, closest. I want a minimum, I want a minimum distance, so this is what I want. Okay, so the points are at plus or minus root 3 over 2, comma, and I need to know the y values there. Let's come over here and check that. So y equals 4 minus root 3 over 2 squared. 4 minus 3/2 is 8 minus 3/2 is 5/2. So plus or minus root 3 over 2, comma, 5/2. So this is my the points that are closest. Now, if I needed to actually find what the distance was, I would be plugging that back into my original distance formula, but it doesn't ask me for that. It just asks which ones are the closest. So the fact that this number is less than this was enough to know that my x equals 0 point is not the one that is the closest. Okay, one more here. For the last one, we have 2 posts. It says one is 12 feet high, the other is 28 feet high, and they are 30 feet apart, steadied by 2 wires attached to a single stake running from ground level to the top of each post. And we want to know where to place the stake to use the least amount of wire. Okay, so let's get a picture. We have, this can be the ground, and we have a 12-foot stake and a 20, that's pretty vertical, that 28-foot stake. Probably not drawn to scale, that's okay. And they are 30 feet apart from each other, 12 feet high, 28 feet high. Okay, so the wire is coming between the top of this one, touching the ground somewhere, and then going up to here. So this is the wire. Oh, let's make that one a straight line too. There we go. Nice. Okay. We are trying to minimize the amount of wire and figure out where along the ground we need to place it. Okay. So we are trying to minimize, I'm going to use capital W for the amount of wire. And the amount of wire is, it's this length plus this length. So we need some variables there. I'm just going to use A and B. So I'm going to call this A plus B. So we're trying to minimize the length of the wire W, which is the sum of A plus B. Okay. Now, we need to get all this in terms of a single variable. So we do have 2 right triangles. Right triangles should make us think either SOHCAHTOA, or if angles are involved, or Pythagorean theorem. So I'm going to call, we're using Pythagorean theorem since we're talking about the lengths. So I'm going to call this side x, and I'm going to call this 30 minus x. So what that will allow me to do is use a Pythagorean theorem expression to write A in terms of x, and then also write B in terms of x. So A is the square root of 12 squared plus x squared, and B is the square root of 28 squared plus the quantity 30 minus x squared. And if I was doing this by hand, I would do some simplifying there, like I would expand this, combine the 28 squared and the 30 squared, but I'm going to be using a calculator, so it doesn't really matter. Okay, so minimizing A plus B, which is root And I mean, I do know that 12 squared is 144, but I would rather not make any mental math mistakes if I'm going to be using a calculator anyway. So 12 squared plus x squared, and then plus the whole quantity 28 squared plus 30 minus x squared. Okay, and I can shift that over a little bit to fit. Okay, so what do I need to do? I need to, I'm going to plug this into a calculator. Okay, now could I do the derivative by hand and then set it equal to 0 and such like we did with the can problem? I could. It's not a big deal though. So let's just go ahead and do this one on the calculator. So we're going to do the square root of 12 squared, which I'm going to put 144, plus x squared, and then outside the radical, plus the square root, oops, the square root of 28 squared plus the quantity 30 minus x squared. Okay. And then I'm going to find the minimum of this. And yes, I can use a derivative and use the power rule and set it equal to 0 on a calculator, chain rule and set it equal to 0 on a calculator, but I'm not going to worry about that. Let's change our window though. Oops, where'd my graph go? Okay, let's get the graph back. Okay, let's change the window. Let's do, what do we know? We know that x has to be between 0 and 30. Okay, so let's go -10 to 40. And then just to be a little outside that, we don't have to though. And then for our vertical, I really don't know what that is going to be because it's about the total length and those might be kind of long. So I'm going to guess that 10 is probably not high enough though. Let's go to 100 and then we can change things if we need to. And then we can make this 10. Also, if you have any kind of function where it's going to graph slow, change your x resolution to like a 2 or a 3 and it will graph a lot faster. Okay, let's try this. Oh, we can see it. Okay, perfect. So it looks like we're going to have a minimum right in here. So let's go ahead and calculate that. Minimum. I'm watching my y values. They're going down. Oh, it looks like it's going to be 50. Now we've gone back up a little bit. So down and then back up. So I know I passed it. Guess. All right. Oop, that looks like a 9 to me. Okay. So let's clip that. So from the graph and our calculator, we can see that the minimum is at x equals 9. Okay, so in other words, that means, so we're going to say 9 feet from the 12-foot pole is our minimum. Okay, does it ask us what the total distance is? Nope, so we don't need to plug 9 back into A and B. So that's it.